What we're going to do in this video is think about a special class of functions where the rules actually change depending on the input value we drop into the machine. While many of the functions we've practiced, like linear or quadratic functions, are defined by a single equation for their entire domain, real-world scenarios often require more flexibility. Think about income tax brackets, electricity pricing, or even shipping costs. The rate you pay often changes once you cross a certain threshold. By the end of this lesson, we'll know exactly how to interpret, evaluate, graph, and determine the domain and range of these piecewise functions. All right, let's look at the notation on our screen. A piecewise function is usually written with a large curly bracket, where each mathematical expression is paired with a specific condition. You can think of these as a set of directions. You only follow a rule if your input, x, satisfies the condition written beside it. For example, here we have f of x equals x squared whenever x is less than 0, and 2x plus 1 if x is greater than or equal to 0. Here, this function consists of two pieces. Each piece has two parts, a mathematical expression, such as x squared or 2x plus 1, and the condition that tells us when to use that expression. I encourage you to pause the video now and think about which branch we should use if our input is x equals -2 versus x equals 0. All right, let's walk through that together. The first one is f of -2, or the value of f of x when x is -2. To find f of -2, we first look at our conditions. Since -2 is less than 0, we must use the top piece, which is x squared. Substituting -2 for x, we will find -2 squared, which is 4. Hence, f of -2 is 4. Now, let's find f of 0. Since 0 is not less than 0, it does not satisfy the first condition. Instead, it satisfies the second condition, x greater than or equal to 0. Therefore, we use the expression 2x plus 1. Therefore, our solution will be determined as 2 times 0 plus 1, which is equal to 1. Let's make sure we're following this properly. Even if a number is right on the boundary, like x equals 0 in our example, we only use the rule whose inequality includes that value. In this case, the one with the equal to bar, 2x plus 1. That means we use the expression 2x plus 1. In general, the conditions in a piecewise function should be mutually exclusive, meaning that each value of x satisfies only one condition. If a value of x satisfies more than one condition, and those conditions produce different outputs, then the piecewise relation is no longer a function, because a single input would be assigned more than one output. Now, suppose our previous piecewise function looked like this, where 0 satisfies both conditions. In that case, when x equals 0, the first piece gives f of 0 equals 0, while the second piece gives f of 0 equals 1. So the same input, 0, is assigned to two different outputs. That means we have two different values for a single member of the domain, which violates the definition of a function. Let's look at another example. Here we have a piecewise function with three pieces, a quadratic function, a linear function, and a rational function, defined as shown. We are asked to find f of -5, f of -2, f of 2, and f of 4. Let's solve them one at a time. The first one is f of -5. First, we need to determine which interval -5 belongs to. Since -5 is less than -2, we use the quadratic expression, x squared minus 4x plus 1. Substituting -5 for x, we get -5 squared minus 4 times -5 plus 1. Now let's simplify. -5 squared equals 25, and -4 times -5 equals 20. Adding everything together, we have 25 plus 20 plus 1, which equals to 46. Therefore, f of -5 equals 46. The second one is f of -2. Here, -2 does not belong to any of the conditions, so it is excluded from the function. Therefore, f of -2 is undefined. Notice that a piecewise function may exclude certain values of x. Whenever a value is not included in any of the conditions, the function is undefined at that value. The third one is f of 2. Since negative 2 is greater than 2, which is less than 3, the input 2 satisfies the second condition. So we use the linear expression 3x plus 2. Substituting 2 for x, we get 3 times 2 plus 2 equals 8. Therefore, f of 2 equals 8. Finally, let's find f of 4. Since 4 is greater than 3, we use the rational expression. Substituting 4 for x, we get 4 plus 1 over 4 minus 2. The result will be 5 over 2. Therefore, f of 4 equals 5 over 2. Now, once we're comfortable evaluating piecewise functions, we need to think about their domain and range. This is where we have to be careful about whether the endpoints are included. We use square brackets for closed intervals where the endpoint is included, and parentheses for open intervals where the endpoint is excluded. The domain is simply the union of all the values where the function is defined. For our first example, the function is defined for all values less than 0 and for all values greater than or equal to 0. Therefore, the domain is the union of minus infinity up to 0 and 0 up to positive infinity, which is the set of all real numbers, or minus infinity comma infinity. Now let's look at our second example. The domain is the union of all the intervals specified by the conditions, which is minus infinity up to minus 2 with open interval, union minus 2 with open interval up to 3 with open interval, union 3 with closed interval up to positive infinity. Notice that negative 2 is excluded because it is not included in any of the conditions, while 3 is included because of the third condition. Hence, we can write the domain as the set of all real number except negative 2, or in interval form as shown. All right, now let's see how we determine the range of each function. The range consists of all the actual output values that the function produces. Just like the domain depends on which input values are included, the range depends on which output values are actually reached by the function. For example, if a piece does not include a certain input value, such as x equals 0 in the first condition of example 1, then the output produced by that input from that specific piece is not included in the range of that piece. However, we must still check whether another piece produces the same output. Based on this idea, let's determine the range of the two examples we looked at earlier. Similar to finding the domain, the range of a piecewise function is the union of the ranges of each individual piece. Therefore, we first find the range of each piece separately and then combine them. Let's see this in our first example. For the first piece, we have x squared for the interval of minus infinity up to 0. Since x squared is a function of an upward parabola, when x approaches to minus infinity, f of x will approach positive infinity, as we had seen in our previous video of graphing a quadratic function. I'll put the link down in the description. We will also plot the graph of each piece here so that you can clearly see what is happening. In many cases, finding the domain and range becomes much easier when we analyze the graph. All right, since we know the upper limit of our range, now let's find x2 value when x equals 0. When x equals 0, f of 0 is also 0. Therefore, the range of the first condition will be 0 in open interval up to positive infinity. The second range will be the range of the linear function on the interval from 0 to infinity. Since the function is linear in this interval, we know the graph will be an increasing line because the coefficient of x, which is 2, is positive. So as x approaches infinity, f of x also approaches infinity. Therefore, f of 0 will be the minimum value of the equation f of x equals 2x plus 1. So when x is 0, f of 0 will be 1. Hence, the range of the function on the second condition will be from 1 in closed interval to positive infinity. Because x equals 0 is included in the interval, the output value 1 is also included in the range. And that happens to be the subset of the range of the first condition, 0 in open interval up to positive infinity. Therefore, the total range of the function will be 0 in open interval up to positive infinity. All right, now let's do the second example using the same approach. So we determine the range of each individual piece and then find their union. The first is a quadratic with positive leading coefficient defined on the interval from -infinity to -2 in open interval. Since the parabola opens upward, as x approaches negative infinity, f of x approaches positive infinity. When the piece is quadratic, the extreme point, which in this case the minimum point, is the vertex. So we look for the vertex for being in the stated interval. We find the x value of the vertex by the formula -b over 2a, which is minus of -4 over 2 times 1, which is 4 over 2, resulting 2. So now we know the quadratic function is at its minimum when x is 2, but 2 is not the member of the stated interval, from -infinity to -2 in open interval. This means the minimum of the quadratic function will be at f of -2, since that is where the graph stops decreasing. So when we evaluate f of -2, we get -2 squared minus 4 times -2 plus 1, which gives 4 plus 8 plus 1, resulting 13. Therefore, the range of the first condition will be from 13 in open interval to positive infinity. The second piece is a linear one, which is an upward sloping graph, so we just find the extreme points, f of -2 and f of 3. F of -2 will be 3 times -2 plus 2, resulting -4, and f of 3 will be 3 times 3 plus 2, resulting 9 plus 2 equals to 11. Therefore, the range of the second condition will be -4 up to 11 in open interval. The third condition is the rational function, f of x equals to x plus 1 over x minus 2, on the interval 3 up to positive infinity. As x approaches to infinity, the number 1 and 2 will almost be nothing compared to infinity. Therefore, f of x will approach to 1, but it will never be 1. So for the value of infinity, we'll have 1 in open interval. We'll see the concept of approach and limit in our Introduction to Calculus video. All right, now let's see the value of f of 3. When x is 3, f of x will be 3 plus 1 over 3 minus 2, which results 4 over 1, which is 4. Therefore, the range of the third condition will be 1 in open interval up to 4 in closed interval. And this happens to be a subset of the range of the second condition, -4 up to 11 in open interval. We can see how it is a subset by locating both intervals on the number line as shown. Here, as we can see, the interval from 1 to 4 is located inside the interval from -4 to 11. That's why we say it is a subset. Finally, we'll find the general range of the function by finding the union of the first and the second condition as shown here, since the third condition's range is included under the second. Therefore, the range will be -4 up to 11 in open interval union 13 up to infinity in open interval. All right. Now we'd seen how to evaluate the solution of a piecewise function and also how to determine their domain and range. Let's proceed to see how we can plot a piecewise function's graph. Graphing a piecewise function is like assembling a puzzle because we plot each piece only over its specific interval, and after finishing graphing each piece, will we find the graph of the complete function. Let's see how we graph this kind of functions with our two examples. Our first function is x squared when x is less than 0 and 2x plus 1 when x is greater than or equals to 0. So first we plot the graph of x squared on the specified interval. When x is 0, f of x is 0, but since 0 is not included in the interval, we plot it in open circle. This shows the point is not part of the function graph. Then as x approaches to -infinity, f of x will approach to positive infinity. So after locating additional points to guide our graph, we will plot the half of the parabola as shown, since the function f of x is only defined as x squared in the interval -infinity to 0. On the second interval, f of x is defined as 2x plus 1, which is linear, so we'll find f of 0 and start our straight line graph from there, connecting the dots. If you want to jog up your memory on how to plot the graph of a linear function, I'll put the video link where we'd seen it in detail down the description. F of 0 will be 1, which is the y-intercept. Therefore, we plot the point. Since 0 is included in the interval by closed interval, we will use closed circle as show where the point is defined in the function graph.
Now we plot additional points as shown and plot the graph while connecting each point as shown here. And just like that, we plot the graph of our piecewise function. All right, let's see the function on our second example. The first piece is a quadratic one, which will have a parabola graph as shown. But the interval is defined at -infinity to -2 in open interval, so our graph will stop at the point -2, 13, where the point -2, 13 will be an open circle, since -2 is not included in the interval here. The second piece is the linear equation, which is f of x equals to 3x plus 2. Here, our graph will be as shown. But the function is defined as such in the interval -2 to 3 in open interval. Therefore, the point -2, f of -2, which is -2, -4, and the point 3, f of 3, which is 3, 11, will be the limiting points for the linear graph in the piecewise function as shown. Therefore, we'll disregard the rest of the points and keep the one on the interval. Both limiting points will be illustrated in an open circle because our interval is an open one as stated in the function. The third one is the rational function, f of x equals to x plus 1 over x minus 2. The graph of the rational function is as shown here. We'll see how to graph a rational function in the coming videos, so don't worry about it. Now that we got the rational function graph, we will keep the section of the graph in the defined interval and disregard the rest as shown. And just like that, we did our piecewise function graph with 3 pieces. We can check the domain and range we found earlier in the graph if it really checks out. The fundamental thing you need to note here is, graphing a piecewise function requires knowing how to graph different kinds of functions, such as linear, quadratic, polynomial, rational, and so on, because each piece of the function can be expressed in any form of those functions. If any of these steps makes a confusion or you need additional elaboration, let us know on the comments section. Hopefully that makes some sense and shows you how these separate rules come together to form one complete relationship. Piecewise functions are powerful tools in economics and calculus because they model the jumps and changes we see in the real world. Just remember, check your condition first, watch your inequalities, and use those open and closed circles on your graphs. And we're done. If this walkthrough was helpful, hit that subscribe button to keep mastering functions with us here at Rimetric Walkthrough. Thanks for watching, and I'll see you in the next video.